Hello and welcome back to another Orange Coast College mathematics video. In this video we're going to talk about polar graphs, and in particular we're going to talk about some really common ones that are going to show up a lot. So starting off, we're going to look at circles and lemniscates. So when dealing with circles, we're going to have one of two equations. We're either going to have a cosine theta or we're going to have a sine theta. Now, depending on whether it's cosine or sine, it's actually going to dictate whether we're on the horizontal axis, being our polar axis, or the vertical axis, being our pi over 2 axis. Now, for both of these, A is going to dictate how large our circle is, as in how big is our diameter. Now, if I'm dealing with cosine, it's going to point to the right, and it's going to be on the horizontal axis. However, if I have a negative sign out in front, we're going to switch the direction. So if I'm dealing with cosine and now it's a negative cosine, we're still going to have a circle, but it's going to go out to the left. The same thing happens with sine. Sine is going to deal with circles being on the vertical axis, but if I throw a negative sign out in front, it's just going to be in the downward direction. Moving on, we're going to be dealing with these graphs that look like infinity signs, and they're going to be called lemniscates. Now, lemniscates are really recognizable because they have an r squared. So immediately if you see that r squared, you should be thinking lemniscate. Now, lemniscates are either going to be on the horizontal axis or they're going to be on the diagonal. Now, in the case of sine, we're going to be dealing with a lemniscate that is going to be diagonal. So, for example, we have this one right up here. It's going from the bottom left to the top right. Now, it's going to have a length, and that length is going to be A. And if I were to put a negative sign in front, this is going to be on the other diagonal. So it would be going from the top left to the bottom right. Now, the same thing happens with cosine, except it's directly on our axes. So it has a length of A, and if I put a negative sign out in front, it's going to put it on the vertical axis. Moving on to our next category of graphs, we have Limacons. Now, Limacons are going to take the form of A plus or minus B sine or A plus or minus B cosine. So there are 4 different kinds of Limacons that we're going to be talking about. And each of these Limacons can be pointed in any one of the compass directions. So let's first talk about the direction in which they point. Now, what do I mean by the direction that they point? I mean this right here. So this is a Limacon, and I would say that this is pointing kind of upward. Now, technically, there's little bits right here that are on the other side, but the majority of the graph is kind of going in that upward direction. So I would say this is pointing in the upward direction. Now, just like the circles, the Limacons are going to follow a similar pattern. Sine is going to kind of be on our vertical axis, and cosine is going to be on our horizontal axis. Now, starting with sine, if our Limacon is pointing in the upward direction, that means it's sine, and it's going to be positive sine. So we'll have A plus B times sine of theta. Now, if it's pointing downward, it's still sine because it's on the vertical axis, but now I'd say it's A minus B sine. If it's on the horizontal axis, we're going to be dealing with cosine. So if it's pointing to the right, we're going to be dealing with kind of that positive version. So we'll have A plus B cosine theta. And if it's pointing to the left, we'll have A minus B cosine theta. Now, the 4 kinds of Limacons that we're going to be talking about, they all differ because of the ratio of the coefficients A and B. So, if A divided by B is less than 1, we're going to get this Limacon right here. Now, the identifying part about it is that it actually has this little loop in the center. And so we would call this a Limacon with a loop. Now, there are some important characteristics about this. For example, these points right here are all going to be important for us. So what are these points? The point to the left is going to be A. The point to the right is also going to be A. The point on the loop is going to be B minus A. And then the point up top is going to be B plus A. Now, this is a good time to note that B and A, even if they are negative numbers, we're going to treat them as positive when we're doing this ratio. So, let's say that A was negative 3 and B was positive 4. We're still going to treat A as positive 3. The same thing is going to occur when we're looking at these points right here. So, the absolute value of B minus A would be positive 4 minus positive 3. And so we would get 1 for the point on the loop. And then for the point up here, we would get 4 plus 3, which is 7. So those are kind of our important points on a Limacon. Moving to the next case, we have the situation where the ratio of A and B is equal to 1, as in A and B are the same number in magnitude. Now, this one has a special name. It's called a cardioid. This one is called a cardioid because if you turn your head a little bit, you'll be able to see that this one kind of looks like a heart. And so we call it a cardioid. Now, those same points are still going to be the same. So right here, we're going to have A. Up here, we're going to have A. Here, we're going to have A plus B. Now this point right here is kind of where our loop should be. Now if A and B are equal to each other, and this is B minus A, what's going to happen? Well, we'll have 3 minus 3, or 5 minus 5. So we're actually going to get a radius of 0, as in this should be on the pole itself. So oftentimes people won't even write it, but we'll still leave the B minus A there, just for consistency. Moving on to the next case, we're dealing with ratios that are between 1 and 2. So A is bigger than B, but it's not twice as much as B. In this case, we actually kind of get a little dimple right here. So we call this one a Limacon with a dimple, or a dimpled Limacon. Now the points still follow the same pattern. We have A up here, we have A over here, we have A plus B. Now right here, this kind of dimple is still going to be the absolute value of B minus A, but it's going to be in the opposite direction to which the Limacon is pointing. So in this case, our dimpled Limacon is pointing to the right. So the dimple is going to be to the left. Moving on to our last case, we're dealing with ratios of our coefficients that are greater than or equal to 2. If this happens, it's called a convex Limacon. Now again, the same pattern will follow for the points. This is still going to be A. This is also A. This is going to be A plus B. And this right here is going to be the absolute value of B minus A. This is going to be in the opposite direction from which the Limacon is pointing. Now, convex Limacons may seem a little weird. They almost look like circles, and in fact, they're very close to them. However, what happens is this side right here ends up being a little bit flatter than it should be to be a circle. It's almost like you took a small ball of dough and set it on the counter for a second. That bottom part would flatten out, while the top would still stay more circular. So it's not quite a circle, it's almost a circle. The next set of graphs that we're going to look at are called rose curves. Now, rose curves typically look like flowers, or they might even look like four-leaf clovers, and some people refer to them as such, but in general, we refer to them as rose curves. Now, each of these is going to be called a petal. And so we would say that this one on the left has 4 petals, and this one on the right has 8 petals. Now, we have sine and cosine just like before. However, this time we're not just dealing with theta, we're dealing with n times theta. And n is where things really start to differ. If n is even, we're actually going to have 2 times n leaves. So in this case, when n is equal to 2, we're going to have twice as many leaves. So we have 2 times 2 is 4. 1, 2, 3, 4 leaves. Now in this case, we have n equals 4. And how many leaves do we have? 1, 2, 3, 4, 5, 6, 7, 8. 8 leaves. Now, if we have cosine, we're always going to start with a petal being on our polar axis, on our horizontal axis. Whereas if we have sine, it's not going to start on our horizontal axis. It's going to start somewhere in between our horizontal and vertical axes. Now, where does it start if we have sine? The first petal is going to be at pi over 2 times n. So, in this case, when we have n is equal to 2, we have 4 leaves. My first leaf is going to be at the angle pi divided by 2 times 2. So it'll be at pi fourths, which is 45 degrees, which is what we have right here. Now, in the case of both sine and cosine, the length of our petals is going to be equal to a. Now, what happens if n is odd? If n is odd, we're going to have the same amount of leaves. So in the left case, we have n is equal to 3, and how many leaves do we have? We have 1, 2, 3 leaves. On the right side, we have n is equal to 5, and we have 5 leaves. Now the same thing happens with cosine. Cosine will start on the polar axis. Now, just like when n is even, sine is not going to start on the polar axis. The first petal is going to occur at pi over 2n. And again, the length of our petals is still going to be a. Now, the first petal appearing at pi over 2n might not make a lot of sense, but let's think about it for a second. If we look at the right side, we're saying that this is r equals a times sine of n theta, where n is equal to 5. So let's rewrite that, and let's pretend that a is equal to 1, just to simplify things. So we have r is equal to sine of 5 theta. That is our function, and that gives us this graph right here with 5 petals. Now, this petal right here is achieving its maximum value at some point. Well, how do I achieve the maximum value of sine? First off, what is the maximum value of sine? The maximum value of sine is 1, and where does that occur at? It occurs at pi halves. So I want 5 times this angle to be equal to pi halves. Now, if I plug in pi over 2n, let's see what happens. It'll be sine of 5 times pi over 2 times 5. Now these 5s would cancel out, and what am I left with? I'm left with sine of pi halves, as in my maximum value of sine. So I get the farthest point away, the tip of the petal, when I maximize sine. And the first time that occurs is at pi over 2n. Once you've figured out where your first petal actually starts, then you just have to say, well, how many petals do I have? And then you divide it up evenly between the 360 degrees, or the 2 pi radians that there are. So we have 5 petals. I'm starting over here. If I divide 2 pi by 5, we're going to get 2/5 pi. So every 2/5 pi, we're going to move over, and that'll be our next petal. And then we'll move another 2/5 pi over, and we'll get our next petal. Another 2/5 pi, we get our next petal, and so on and so forth. And then finally, we will have constructed all of our petals, and we'll end up back where we started. Now, before we move on, let's take a look at something. Let's take a look at this graph on the left. This graph looks pretty symmetric to me. If I cut it in half down the middle, it looks like the right side is symmetric to the left side. And the same thing happens if I were to cut it the other way, and I cut it along the horizontal axis. It looks like the top side would be the same as the bottom side. Even the diagonals look like they would be symmetric. So the next question is, since we have symmetries with normal functions in the Cartesian plane, is it possible that we can have rules for symmetry dealing with polar graphs? And the answer is yes. Now, there's going to be three kinds of symmetry that we're going to look at. There's going to be symmetry over the polar axis, being the horizontal. There's going to be symmetry over the pole, which is kind of like our origin symmetry. And then there's going to be symmetry over the vertical axis, being the pi/2 axis. Now, what is the rule to test whether we have symmetry over the polar axis? Well, if our function r is equal to f of theta is unchanged when we replace theta with negative theta. So if I replace theta with negative theta instead, and nothing ends up changing about my function, as in I use some identities or something like the sort, and I can get back to my original equation, then I have polar axis symmetry, or symmetry over the horizontal axis. Now moving on to the pole, we have symmetry about the pole if our function r is equal to f of theta remains unchanged when replacing theta with pi plus theta. So, if I replace my theta, my angle, with pi plus theta, as in take my angle and add 180 degrees to it, if nothing changes, then we have symmetry about the pole. Now again, you're probably going to have to use some identities to actually solve this, but we'll get to that later. Now looking at the pi/2 axis, or the vertical axis, we have symmetry about it if our function r is equal to f of theta is unchanged when replacing theta with pi minus theta. So if I replace theta with pi minus theta, or 180 degrees minus our angle, and nothing changes, then we have symmetry over the vertical axis. Again, we're probably going to have to use some identities, but we'll deal with those when we actually get to them. Okay, that's going to do it for the first part of this topic. In the next video, we're going to see how we can take all of the stuff that we just learned and apply it to sketching. So, I'll see you there.